Welcome to Group Theory. Today, we are going to explore a fascinating concept called automorphisms of cyclic groups. Imagine you have a perfectly symmetrical clock face and you want to rewire its internal gears so it still works exactly the same way but with the numbers swapped around. How do we do that without breaking the fundamental math of the clock? That careful rewiring is exactly what an automorphism is, and by the end of this video, you will understand exactly how it works. Now that we have our clock analogy, let us define our terms formally. First, a cyclic group is a mathematical set entirely generated by repeatedly combining one single element, which we call the generator, with itself. Next, an isomorphism is a strict one-to-one mapping between two different groups that perfectly preserves their structural rules. So, what happens when the starting group and the ending group are exactly the same? That is an automorphism. It is a mathematical function that maps a group onto itself while keeping its cyclic nature completely intact. With our definitions clear, let us look at the mathematical representation. We write our cyclic group as G, and the letter A inside angle brackets represents its generator. This notation simply means that every single element inside the group G can be created by taking the element A and combining it with itself repeatedly. If the group has a finite size, repeating A enough times will eventually loop back to the starting point, much like walking around a circular track. Understanding this notation is the first step to seeing how the entire group moves together. Knowing how the group is generated leads us to the core property of an automorphism, denoted by the Greek letter alpha. The variable x represents any whole number, meaning a to the power of x is just the generator a repeated x times. This formula states that mapping the combined element gives the exact same result as taking the mapped version of the generator, alpha of a, and repeating it x times. This proves that the entire mapping function is completely determined by just knowing where the single generator goes. If you change the generator, every other element follows predictably. Since the entire mapping depends on where the generator goes, we must ask, where can it go? The output must still be an element inside the same group G. So the new mapped value must be equal to the original generator A raised to some power k. However, for the mapping to cover the entire group without missing any elements, this new element A to the power of k must also be a valid generator for the whole group. Therefore, the entire problem of finding automorphisms reduces to finding all the valid powers k that create new generators. This brings us to the mathematical condition that guarantees our new element is a valid generator. For a group of size n, the greatest common divisor of k and n must be exactly 1. This means that k and n share no common factors other than 1, a relationship known as being co-prime. If k and n shared a larger factor, taking steps of size k would cause you to skip elements and loop back too early, failing to generate the full group. When the greatest common divisor is 1, you are guaranteed to hit every single element. Now that we have our formula, let us see this with a concrete example. We will find all the automorphisms of the group of integers modulo 6 under addition. This is a clock-like system with 6 numbers, from 0 to 5. Our strategy is to first identify the total size of the group, which is n equals 6. Because the group is generated by taking steps of 1, we must find all possible new step sizes k that will still visit all 6 positions before repeating. Continuing with our strategy, we apply the greatest common divisor rule to our specific case. We need to find every positive integer k that is less than 6 and shares no common divisors with 6 other than 1. This ensures that multiplying by k will cycle through all 6 elements without getting stuck in a smaller, tighter loop. If we picked a number like 2, it would only generate the even numbers, completely missing half of the group's elements. The numbers 2, 3, and 4 all share factors with 6, so they fail the test. This leaves us with our valid step sizes. The only numbers that satisfy this strict condition are 1 and 5. Therefore, there are exactly two valid ways to rewire this group without breaking its structure. The first is the identity mapping, multiplying by 1, which leaves everything unchanged. The second mapping multiplies every element by 5. In our 6-hour clock system, this completely shuffles the elements but perfectly maintains the mathematical rules of the group. Let us visualize what we just calculated. Here you see a regular hexagon representing our 6 elements. The red arrows show the standard generator, taking steps of 1 around the perimeter. The blue arrows show our automorphism, taking steps of 5. Notice how the blue path still connects every single point in the system before returning to 0? Any other step size, like 2 or 3, would create isolated triangles or straight lines that fail to cover the entire hexagon. Having mastered finite groups, let us look at an infinite cyclic group. We will use the group of all integers under standard addition. This means the set of all whole numbers stretching infinitely in both positive and negative directions. Because the group is infinite, the concept of wrapping around a clock face no longer applies. However, the core approach remains identical. We must find the generators of the group and then determine which mappings send a generator to another valid generator. Let us formalize this infinite group mathematically. The symbol Z represents the set of all integers. To generate every possible integer using only addition, we must start with a number that can reach any value by repeated addition or subtraction. If we chose a number like 2, we would only ever generate even numbers, leaving out all odd numbers entirely. So we need a step size that covers absolutely everything. Because the set is infinite, our choice of generator is much more restricted than in a large finite clock system. Let us find the specific automorphisms for this infinite group. For the set of all integers, the only elements that can generate the entire set are 1 and -1. Adding 1 repeatedly gives all positive integers, and subtracting it gives all negative integers. The exact same is true if you start with -1. Therefore, any valid automorphism must map the generator 1 to either 1 or -1. This gives us our final mappings for the infinite case. The first automorphism maps the generator to itself, leaving the entire infinite number line completely unchanged. The second automorphism maps the generator to -1. This means every integer x is mapped to its negative counterpart, -x. Visually, this is equivalent to taking the entire infinite number line and flipping it horizontally, like a mirror image around 0. The structure of addition is perfectly preserved. Before we conclude, you might wonder why this matters in the real world. Understanding the automorphisms of cyclic groups is incredibly important in modern technology, particularly in data security. The widely used RSA encryption algorithm relies heavily on the properties of numbers that are co-prime to a given modulus. The predictable, structured behavior of these mappings forms the mathematical backbone of how secure keys are generated, allowing us to securely scramble and unscramble sensitive data across the internet. Let us summarize what we have learned today. An automorphism of a cyclic group is a structural rewiring that is completely determined by where it sends the group's generator. To preserve the group, the generator must always be mapped to another valid generator. For finite groups, this means multiplying by a number that shares no common factors with the group size. For infinite groups, it simply means choosing between the positive and negative direction. You now understand the fundamental mechanics of cyclic group automorphisms.